Yeah, maybe you can sit there. That's my chair. Chair? I'd like to see your Sheldon Cooper. That's fine.
Okay, welcome back to the second session in the morning that I have the pleasure to chair. And the first presentation is again a keynote presentation given by Diederik Jacques on this famous HPX extension of Hydrus.
So good morning again. I will give you a short talk about the generic reactive transport model available within the Hydrus codes, and it's called HP. And we know indicated by X because we have it also for more than one dimension. I will just give you a short overview of some recent developments during the last 3 to 4 years. So the work is done, of course, together with Jutta. And then we have two persons who support us a lot. My former colleague, Mallants, who is now at CSIRO, and then is also very supportive of these developments. And that's my last slide. So I will tell you a little bit about which processes are within the HPX codes, and I'll give you some recent examples. One is on diffusion in the gas phase, which I will illustrate very shortly with an organic matter model for in the soil. I give you one example about the two-dimensional flow and transport possibility now. I give you an example about simultaneously estimation of flow, transport, and geochemical parameters. And I will give you an example on the feedback between change in geochemical variables and transport parameters by precipitation in dissolution reactions, for example. And then I will give you one example about some benchmarking, international benchmarking between different reactive transport codes we are involved in. So, HPX is a numerical tool to simulate water flow, solid transport, heat transport, and biogeochemical reactions in variably-saturated porous media. We have it up to now in 2 dimensions, HP1 and HP2. And basically it is a coupling between 2 existing codes, coupling between the Hydrus codes, on one side to do the flow and transport simulations, and with FreakC, which is a code for doing thermodynamic and kinetic biogeochemical processes. And the coupling is done in a sequential, non-iterative way, meaning that it's first doing all the transport calculations without doing any geochemical calculation, and then doing the geochemical calculation without any transport calculation within a single time step. So as already stated, we can do, so these processes are coupled within this code. So we have variably-saturated water flow described by the Richards equation with fluid water uptake. We have the convection dispersion equation for solid transport and for heat transport. And then there is a possibility to calculate thermodynamic equilibrium reactions, but also to do kinetic reactions. With the possibilities of Hydrus, we can handle these type of systems. So we can have uniform flow and transport models. We have a 3-phase system in a porous media: the solid phase, gas phase, and an aqueous phase. And then we can do different transport simulations of water flow, of heat. We have advection dispersion in the aqueous phase and diffusion in the gas phase. Then we have some homogeneous reactions, sink source reactions in the aqueous phase, uptake of water, uptake of nutrients by plants, and then we have degradation, decay, and transformation reactions within the aqueous phase. For example, radioactive decay, all kinds of reaction networks. Basically, all these things are also in Hydrus. The main difference now is that you can have different reaction networks, and not only a sequential network. And then we have heterogeneous mass exchange processes. We have the equilibrium exchange between the gas phase and the aqueous phase, and then we have kinetic and equilibrium exchanges between the aqueous phase and the solids phase. And these exchange reactions, I will come later on which processes are included. Because Hydrus is so advanced in water flow and solid transport modeling, within the same system we have also the physical non-equilibrium model included. It's just the water phase and the solid phase we can divide in a mobile and an immobile domain. Basically, there is one additional physical exchange process between the mobile and the immobile region, and then basically all other processes are the same, except we have also mass exchange reactions between the immobile water and the solid phase in contact with the immobile water. And then the last variant is the dual porosity model. Basically all the same processes are there. The only extra one is that there is a water exchange term between the water between the aqueous phase, between the mobile and the immobile aqueous phase. Then, with respect to thermodynamics, what kind of processes are in there? So that's then all the profit we can take from all the processes which are in the frequency. So there is aqueous speciation calculations, and there are different activity correction models. So the low ionic strength models like Davis, W. Huckel, and B. Dot. But in frequency you can also have the high ionic strength activity correction models as Spitzer and an ion interaction model. Secondly, you can describe sorption to the solid phase by cation and anion exchange reactions, and it's possible in frequency to use different conventions for defining the activity of the exchange species. For example, the Gabon or the Gay-Thomas, but you can also have it in such a way that the selectivity quotients change with the mole fraction of your cationic and your anions on the exchanger, and then you can use, for example, the Rotman-Kornfeld model or the active fraction model. That means that when you have a very low mass fraction of a given cation, selectivity is mostly very strong, so that's kind of nonlinear stuff. You can have multiple exchange sites linked to different groups, to different minerals, and so on. And you can link the capacity to the amount of equilibrium phases or kinetic reactants in your system. And if this amount is changing by dissolving or precipitation reaction, then also the amount of exchange sites will change. Next process is the surface complexation models. There are three different models in frequency: non-electrostatic model, the diffuse double layer model, and the CD music model. And you have different options to calculate the composition of the double layer. As with the exchange processes, you can have multiple surface complexation types, and you can also have it linked with equilibrium or kinetic reactants. Then you have equilibrium, dissolution and precipitation of minerals in your system. You can describe solid solutions, and you can have exchange with the gas phase. So these are all equilibrium reactions. And then you can also include all kinds of kinetic processes. So you can, for example, you do not want to have equilibrium precipitation of a given mineral, but treat it in a kinetic way. For example, you can base it on the transition state theory. And here you see the rate as a function of the saturation index of a given mineral. So because it's negative, the mineral is undersaturated and will dissolve. If you are far from equilibrium, so equilibrium is when your saturation index is 0. If you are far from equilibrium, you have a constant dissolution rate, but when you reach equilibrium, your dissolution rate will decrease. So you can also include kinetic sorption and desorption processes, kinetic exchange processes, and things like that. And then you can also have these kinetic degradation and transformation processes within the aqueous phase, described by first order reactions or mono or Michaelian's method kinetics. Oh, I thought I had one. I know, but I'm going backward. And here, that's, for example, the implementation of a monokinetics. where we degrade phenol as a function of time. Again, when you have a high phenol concentration, your rate is linear, first order, but when concentration becomes very low, you have also a change in this rate. You can include kinetic reaction networks. So basically what is known in Hydrus is just a sequential network going from here to here to here to here. But we can have also parallel networks within this possibilities that we see. And then, for example, this is the network of PCE, where we have initially only PCE in there, and then it degrades and it produces all these other components, and they all have a peak, and then maybe they are disappearing again. You can also include bio elements into these kinetic reactions. For example, this is the degradation of an organic compound, and the rate of this degradation depends on the concentration of the substrate, but also of the amount of biomass in your system. And on the other hand, when you are degrading this component, the biomass gets energy, so it can also grow. And so you see this grow in biomass. Then at the end, all your substrate is gone, and your biomass start to decline because of that. So these things can also be included in the model straight away. And then, and that was on the poster yesterday, we can also include active food uptake of nutrients of species. And what is the difference with the implementation in Hydrus is that you can make your parameters dependent on your solution chemistry, if you want to do that. And here in this example, so it was introduced yesterday also, it's the uptake of potassium is simulated for different water treatments, and from treatment 1 to treatment 7, the salinity of these waters increases due to higher sodium concentration, and so that has some limitations that put some solid stress, and the uptake of potassium is smaller when the salinity level is much higher. So with all these things which I discussed now, you can incorporate quite complex reaction networks within this model. And here I have an example of Mercury, and I have another talk within a half hour where I will go into more detail into this model. But basically you see we have Mercury species in the three phases, so in the gas phase, the aqueous phase, and in the solid phase. We have some kinetic reactions, namely the dissolution process of mercury present as an apple, or mercury present in a solid phase. So this will then produce either mercury 0 or mercury 2. We have a kinetic reduction process of mercury 2, and then we have all these equilibrium processes, inorganic speciation, and speciation to organic matter. I will go into more detail on that later on, but basically the flexibility within Freak C allows you to incorporate these kinds of networks. I guess I now will go to some new developments. One is diffusion in the gas phase, and that I illustrate here with this organic matter degradation model developed by Porosity a few years ago. So basically you have three organic pools, litter, carbon, humus carbon, and the biomass. And every year you get some fresh material into your system, and this will degrade the humus, and part of the degradation will turn litter into humus, part of the energy will then go to the biomass, and part will produce inorganic carbon, CO2, which then have the speciation in the aqueous phase, and also the exchange with the gas phase and the efflux to the atmosphere. And so on. So also humus then can degrade up to the biomass, and the biomass will die and will return to the litter pool. So basically we have this set of equations, and you see that all of these rate equations depend on the pool itself and on some other kinetic pools. Furthermore, the rate constants can depend on environmental conditions. So within this model, we implemented the dependency of the rate constant on your water saturation and the dependency of your rate constant on the temperature. None of this is hard-coded. Everything is available. You can define everything via the input file. So you are not sticked to these equations if you think based on your experimental data or your knowledge or your expertise or whatever you want to use other models. You can include them into the input file with small programs like that, and you can use all information about your chemical speciation, temperature, things like that, to define these such types of reactions. So these are the resulting curves. So for the water content, you have an optimal value at a given saturation degrees, and then it decreases at both sides. And at the temperature, you have an increase of the rate with temperature. So we did, it's only an illustrative example, so we didn't have any data here. But so we did a simulation for 1 year. Here you see the water content changes as a function of depth and time, the x-axis time, and also the temperature. And these two information are then used together to calculate the reduction factor or the enhanced factor of the rate coefficients. And you see during this dry period in the topsoil, you basically have no organic matter degradation or cycle anymore. And these things are then transferred to the different organic and inorganic pools. So here you see the change of the litter pool, the change of the humus pool, the change of the biomass pool as a function of time. So they are varying slowly following the seasonal trends, mainly of the temperature. And then this is the CO2 partial pressure in the gas phase at the different depths. So this is also following the seasonal trend, mainly of the temperature, but it's also following the changes in water content during the day. And it takes also into account that the solubility of CO2 is changing with temperature because of the thermodynamic data. The second development finished last year was the extension from 1D to 2D and the incorporation of it directly in the graphical user interface. It's an example which was also on the post roadside. So it's a typical 2D flow region with a saturated water region here going down to the river. And then we have one part where we have a high infiltration rate and very acidic water, and then the rest of the region has a low infiltration rate with water typical for rainwater, with the composition and pH typical for rainwater. Basically, the example is based on work from George J. I don't know if it's really great work, but it was just a very easy implementation that we did here to test the model numerically if it's working in the way that we want to have it work. But basically you see that so the blue is the low pH and the red colors are the high pH. That's the result after 1,000 years. You see the pH bloom which is infiltrating from that zone and it's moving towards the river. The water was polluted with some uranium, so you see also uranium following this plume, but uranium will sort and will precipitate on this path also, and this is not shown here. And because of the very acid pH is infiltrating into soil, calcite in the system is dissolving. Third example is an exercise where we use experimental data to obtain simultaneously flow, transport, and geochemical parameters. The geochemical model was here a cation exchange process. So we calibrated the cation exchange capacity and the thermodynamic constants for that soil. Basically, it was a horizontal soil, dry, which was put into contact with water, so you get water absorption and then the infiltration of some polluted soil, water. Sorry. So I show here the results for 3 times, and it's plotted against the Boltzmann transform. Because it's a diffusive case, you have it all, these curves all fit, collapse on one curve, more or less. So we get a good description of the water content. Also the pure water transport, the tracer transport was simulated quite well. There were some errors in the experimental data, but the bulk data, we followed the bulk data quite well. And then we did that also for the cations, sodium, potassium, magnesium and calcium. So I show you here the results for magnesium. So we were able to obtain parameters and to describe our observations quite well. And we did it with two models. The classical Gapon model used much in soil science, and then the methods which also have this change in selectivity coefficient with the mole fraction on the cation exchange complex. And this model, so the Rückmann-Kornfeld model, performed a little bit better within this region here. Question by optimizing so many parameters is the identifiability of the parameters. So we also made surface plots, contour plots of the objective function. This one here is for the exchange parameters for potassium and calcium within the Gaines-Thomas approach. And for all these parameters within the Gaines-Thomas approach, we get these type of contour functions, so indicating large identifiability of these parameters. For the other one is for the Rückmann-Kornfeld convention, and there for some parameter combinations we had these values which indicated correlation between the parameters and not always optimal identifiability. So, and that was also confirmed in a kind of validation step in another experiment where it was shown that the Gapon was more robust and was better in describing other experiments compared to the Rückmann-Kornfeld parameters. The following example is on changing transport properties in function of your geochemical variables. So HP, basically it should be HPX, allows the dynamic updates of different transport properties, including porosity, soil hydraulic properties, tortuosity of the aqueous and the gaseous phase, dispersivity, heat conductivity, and heat dispersivity. The way we implemented here is that we didn't put any functions relating change in solid phase and change in these parameters into the model. The user has to define his conceptual model, how he sees these relations, and he can implement it via the input file and the basic functions. Okay, so that's because everybody has other ideas how these things are linked, and of course I have no idea how this specificity is linked to precipitation, so I didn't want to do there anything, just allow the possibility. I'll show you a small example on concrete. So basically we have a horizontal concrete beam of 4 centimeters, which is in contact with water, so basically in constant concentration boundary at one side, and so we have the diffusive solid fluxes. And we did the simulations for 3 different water types. Pure rainwater, then we have rainwater also with bulk deposition, dry deposition in it. As a consequence, cations and anions concentrations will be larger there. And then the last one, we call it soil water. Well, that's water where we assume that there is some microbiological activity and the partial pressure of CO2 is about 1 order of magnitude larger than in the atmosphere. And if you do pure batch type of simulations, the soil water is the most aggressive water for leaching out your concrete. So leaching out concrete, meaning removing the calcium from the portlandite. And the last water is the most aggressive one, because it not only dissolves the portlandite, but it also precipitates calcite, because there is a lot of, and so the dissolution reaction of portlandite go fast. I will not go into these details, but concrete is a multi-scale porous media with different porosities, and it has also quite large range of tortuosity factors from low porosity up to porosity where all the hardened cement paste is dissolved. Then you have only aggregates left. Fresh concrete are about, well, the ones we used in the simulation are having porosity about 0.1, and so it changes by, the tortuosity is changing by 2 orders of magnitude. I will give you some simulation results. I don't know if it's maybe 3 minutes, so yeah. So here I show you portlandite dissolution fronts for the three water types, and it's against the Boltzmann constant. But you see that the rainwater is advanced a little bit more than the other two waters. And that's a little bit in contradiction with what I said in the previous slide, that basically the soil water is the most aggressive one. And the reason is found by precipitation of calcite near the boundary. So you see in the soil water we get lots of calcite precipitation there, basically clogging the pores, and so that the dissolution front cannot move much faster anymore. You see also that there is, in the case of the bulk deposition, some precipitation, but that is of magnesium-bearing minerals. So here you see that this calcite produce a reduction both in porosity, but also a reduction in the tortuosity, which will slow down the Portland-like dissolution front compared to the rainwater. But the water is still more aggressive, because before, at positions closer to the boundary, you see that for the red curve, the pH is lower in case of the soil water compared to the rainwater. So in the part before the clogging, of course, the soil water is still much more aggressive and leaching out calcium much faster and decreasing the pH much more. Okay, then we did also some benchmarking at international benchmark, comparing different reactive transport modes. Here is one example where we do, and this benchmarking is quite important to test the numerical accuracy of these methods and models. So it's oxygen diffusion in the soil, together with pyrite oxidation, and there is a groundwater table at 2.5 liters, and we have three codes here. Solid line is for min3p, dotted line is for HP1, and the dashed dot line is for Frootland. And with respect to minerals and pH and PA, and also with respect to CO2 and speciations above the groundwater table, the three codes corresponds quite well. But when the dissolution fronts and things like that hit the groundwater table, the three codes start to divert a little bit. And so there are differences between the three codes at this time, where we use exactly the same input model, so it's numerical differences, but we do not know, of course, which model is the most accurate in this case. So basically that's all what I wanted to tell.
Any questions? Yes.
Yes, regarding the organic matter model, can the model distinguish between the solid organic matter and generation of dissolved organic matter?
Well, this model doesn't have that in it, the one I presented here. But if you talk in generic terms about HP, it's up to the user how he defines his conceptual model and which processes he wants to include. So here it's just all solid organic matter, and there is no transport of dissolved organic matter. So the degradation just goes from one pool to another pool, or to inorganic carbon and CO2. But if you want to say part of the fraction goes into solution.
No, but the kinetic of this process.
Yeah.
From moving from solid organic matter, degradation, dissolved organic matter. Can you do that?
Yes, if you want to do that, you can do that again.
Okay.
If it's not too complex. But yeah, if you can have the additional step of soil organic matter, it's degrading, and part of it becomes dissolved organic matter and then moves into the water of absorbing again. It's possible, but it's not implemented in the example that I showed you. But you can add rate equations to describe that. That's for sure.
And another question: how do you account? Different question.
Yeah.
How do you account for clogging in your
Well, in this example, for example.
Yes, an example. How do you account for clogging? Just changing the porosity in the entire flow domain, or?
Well, for every node, it calculates. Well, in this example here, for every node, it just looks to which solid phases are present, and then it calculates from that the volume of the solid phases and then the porosity. And then we have a model which relates the porosity to the tortuosity and also the porosity to the hydraulic conductivity. Okay. But again, I didn't impose these equations in the source code. You have to define them in the conceptual model, in the mathematical model.
So if you are accounting for particle transport, you can calculate the changes in velocity according to the, say, attachment.
If you can describe your particle transport with its convection dispersion equation, you can.
You scale the velocity according to.
I do not see any. Yeah, in theory you could do that. Okay. Well,
sure.
But it's I don't see why you cannot do it. You just have to define your. The key point of this HQ is that it's more a kind of tool, a framework where you can do your. Then you have to develop your conceptual model about your processes, how you see this particle transport, and then translate it into the rate equation, something like that. Of course, yeah, if you want to describe particle transport in another way than convection dispersion, then it's not possible. Within the framework of the transport equations, you have some flexibility to do different things.
Diederik, in that horizontal absorption cation exchange example, I guess you fitted the water parameters were derived directly from the infiltration.
Yeah, they were also derived from the water content profiles.
So how many parameters could you fit simultaneously to those concentration data? We fitted it in sequence a little bit, and for the water content, because it was disturbed soil, it was repacked soil, we didn't really care a lot about these parameters. We just wanted to have the infiltration front okay, so we didn't care about uniqueness
and things like that. In that, I think the information is not sufficient if you want to have it. The information content in the data is probably not sufficient if you want to have all these parameters in the function. But here it really it doesn't really matter because it was repacked soil, and the main point here was to get the front, the infiltration front. Okay.
Okay, I think I don't see any hands, so I think it's time to move on and give Diederik a break before he comes back. Yeah, we stay with